Okay, so I hope you have read these things. The P type of semiconductors, majority Na atoms, Nd atoms in N type of semiconductor. Okay, Na and Nd stands for what? The atom, the dopants that are added. Na stands for the atoms like boron, trivalent substances. Nd stands for the pentavalent. Okay, fine. So now, so as soon as the metallurgical PN junction is formed, density gradient exists across the junction, etc. All that I have told you in the earlier class. So therefore, the diffusion process starts. Now, how the diffusion process starts? Okay, see the holes from this side will start entering this side. Okay, the holes from this side will start entering this side. But the most important thing is, we are now going to consider those holes from the Na atoms and those electrons from the Nd atoms. Predominantly we are considering that. And as the holes enter from left to right, see, I have marked 4 lines. This is A, this line is B, this is C, this is D, and this is E line. Okay, so this is this line C, it is the junction line. Now the ions, the Nd ions here, okay, they donate the electrons, and the holes that come from this side are trapped by the electrons, the free electrons here, and therefore the most important concept is these become acceptor ions and these become donor ions. And since now they do not have charges, they are all, whatever charges are there, they are bound. Okay, therefore they become immobile charge carriers, but they will contain charge. What I mean is, now that this positive donor ion, it has given out an electron, now it has become a positive ion, and this has become a negative ion, and they are immobile charges. That is most important. Okay. Now, the other issue that I was discussing in the last session was that, see, now if you take this C, if you take this line C, so from this side you see the holes have come to this junction C, and I gave you some number as assume that there are some 1000 holes on this line. Now what happens to these 1000 lines? Because of diffusion, these holes starts traveling. These holes starts traveling towards the towards what? Towards D and E. Towards E they start traveling. But en route they start getting trapped. They start getting trapped, and therefore, if I now plot the density of holes versus X. Okay, so the density of holes versus X at the point C that I am seeing here is, this density will droop down like this. Okay, and this point is something lesser than D. This point is say lesser than D. That is, this point is between C and D. So this is what happens to the hole density. Why it happens is because as the holes are penetrating into the N region, they are getting absorbed. Okay, friends, and the ions are being formed. Hello, are you with me, all of you?
Yes, sir.
Now, further batch of holes, if they try to penetrate, they cannot penetrate. Okay, the first reason is that for the charges to move, there has to be a conductor, or there has to be atoms here which will help the charges to move, or there should be free charges available. Since this region now is depleted of free charges, therefore the diffusion currents cannot move from this point to this point. That is, it cannot cross this point because this region is bereft of the transportation. That is, there are no charge carriers. Okay, this is one point. So therefore, the diffusion, whatever charges had initially come to this layer, only they are percolating inside. That is the point that I wanted to drive to all of you. Did you get it?
Yes, sir.
That is first point. Second, so therefore, this graph, you see this graph till this point, Till this point, the buildup is why because more and more positive ions are created. That is why this buildup takes place. Now, the charge density, the holes that were injected here, they will gradually their charge density will decrease, and then the charge density. See this graph, this line I am showing you here. It is because of the buildup of the positive ions. It is because of the buildup of the positive ions. Okay. Now here you see there are other charges. What charges are there? There are also, see, there are majority charges here are electrons, isn't it? Majority charges here are electrons. So here you see these majority charges now are trying to move towards this side. Why they are trying to move towards this side? Because of
concentration gain.
Yes, because of concentration gradient. So as they are trying to move towards this side, so whatever holes had come this side, some of these holes are neutralized by these charges, by these majority carriers which are moved like this, and therefore you will get a shape like this. Agreed?
Yes, sir. Agreed.
Okay, agreed? Now, the same thing happens to the left, and that is why the charge density is this, and this side negative ions are built up, you will get it like this. So that is the reason why you are getting the graph like this. Agreed?
Yes.
Okay, then. So one major padav is done. Okay. Right. Now, so the injected holes at instant time steadily diffuse from C towards D. During diffusion, they are consumed by Nd atoms, so the number of injected holes steadily decrease, but the positive donor ions increase. Similarly, the injected electrons. I hope you can read this, students. Hello, I am asking you. So here you see the shape of the charge density can be attributed to the above phenomenon. Clear? Okay. The electric field increases from D towards C due to the positive donor ions as a donor ions and is maximum at C. This is because you see if you go on integrating this, from left to right, the intensity goes on, the charge density, the integration of the charge density increases, so therefore the electric field will also increase in magnitude. I am showing it down here because I have taken this direction is positive, this direction is negative. Therefore the electric field will increase. Clear?
Yes.
Further what happens if you go on integrating from this side to this side, so the integration will go on increasing for positive charges, but as you go to this side, the integration is positively increasing, now it starts decreasing and finally becomes 0. That is why you are getting this graph. Okay?
Yes, sir.
Done. So now the electric field intensity graph is like this. Now yesterday, you see, now the electric field is related to the potential field by minus dou V by dou X. Minus dou V by dou X. So minus dou V by dou X, if you see here for the electric field here, okay. If you differentiate this potential, see, if you differentiate this potential curve, then you are going to get the corresponding electric field. Can you correlate these two? My question to you is, how will you relate these two graphs? Okay. Anyway, in the diagram it is not clear, but supposing I had given you this only the electric field, the graph of the electric field. So from this, if I had asked you to get the graph of the potential field, how would you have done that? That's my question. Okay, that is, you see, it's nothing but the slope. So here you see the slope here is maximum and the slope here becomes minimum, negative, isn't it? The slope here is, that is the slope of, the slope of this, sorry, I said the value here is minimum, the value here is maximum. So therefore now this one, if you now have this curve, something like this. So because now here you see that is the potential curve I am telling you. The potential curve I am telling you. The potential curve. The slope of the potential curve is very less here. So the intensity of electric field will also be very less. Correct? And as the slope is increasing here, the intensity will also increase. Correct? So this point corresponds to this point. This point corresponds to this point, and this point corresponds to this point, because the slope, see, this is voltage versus x graph. Okay? Here is the potential, the slope of the potential here is more, no? The slope is less, no. So therefore the corresponding intensity due to this is less. The corresponding intensity due to this slip is more. Correct, no? And negative because it is minus dou v by dou x. Minus dou v by dou x. So the slope, it is more slopey positive. So you will get more negative electric field here.
Yes.
Now further how this curve will go? This curve should go like this. Understood? So the potential curve must be like this and like this. So here it is, the slope is very less, so electric field is also very less. Here the slope is very large, so the electric field is also very large. Correct? Then what happens? The slope here once again starts becoming lesser and lesser. So here it is almost flat. So therefore you will get electric field intensity 0. Correct? It is not a straight line, it is something like this. The voltage versus x. So it is you are seeing it as a straight line, but actually at these points you are getting like this. Got it?
Yes, sir.
So that is the potential energy. Now here you see as potential, there is something called as potential barrier. Okay. Now I will elaborate that in the next section. Next section. But right now keep this graph live. I will explain that in detail. Okay. We noted that the above described donor and acceptor and immovable charges are created and destroyed. Due to this, there are diffusion and drift currents. That is, it is not that, see, the diffusion, these currents are continuous, right? But the sum total of them under thermal equilibrium is 0. I have told you this yesterday, and that is mainly because you see, these immobile charges are formed here. That doesn't mean permanently they will be immobile and they will be there. They will make and break, keeps on happening. Okay, so therefore you will have the diffusion and drift currents continuously happen. At thermal equilibrium, the diffusion and drift currents are equal and opposite and constant. I have explained to you dynamic equilibrium. The currents across the junction will neither rise nor fall as there are no mobile charge carriers. The currents across the junction will neither rise nor fall as there are no mobile charge carriers in the region between B and D to transport the charges. The region BCD is depleted of mobile charges, and it is called depleted region or space charge region. Clear?
Yes, sir.
If the doping constant, now see, if you have understood all this, then you can answer these questions. If the doping concentration is increased, more number of immobile charges are created just in the vicinity of C, and rapid reduction of the number of injected minority charges at T is equal to 0 before they reach B and D. This point is B and this point is B, C and D. So more charges, if the doping concentration is increased, then more number of immobile ions are created just in the vicinity of C, and rapid reduction in the number of injected minority charges at T is equal to 0 before they reach B and D. Hence, the width of the depletion layer decreases with increase in doping concentration. Did you understand this point?
No, sir.
Okay. So now see, if what I was trying to tell you, whatever charges were injected here, whatever holes came here, you know, these holes, the density of these holes went on decreasing like this. I hope you remember just now I told you this.
Yes, sir.
Why? And you see why the density is decreasing like this of the injected holes.
Because they are trying to diffuse, sir.
Oh man. Why? See, you are not following here. See, now initially 1000 holes came to this line. I told you that example.
Yes, sir.
And as they tried to percolate inside, they started getting consumed by the free electrons on that side, isn't it?
Yes, sir.
The amount of consumption, that is amount of disappearance of the injected holes, depends upon the concentration of the pentavalent dopant. If the concentration of the pentavalent dopant is more, then within a short duration, many of these injected charges will be consumed. And therefore, this width will reduce. Okay?
Okay, sir.
Okay?
Okay, sir.
Hence, the width of the depletion layer decreases with increasing in doping concentration. Okay?
Yes, sir.
Now, the charge density around B and D, this is B and D, due to the minority charges pulled from AB and DE regions respectively. At that time, see, the charge density around B and D due to the minority charges pulled from A. So this point is A and this point is B. Okay, the charge density around B and D due to minority charges pulled from the regions A and AB and DE regions respectively. As temperature increases, the minority charge concentration increases and also their kinetic energies. This will create more negative and positive mobile ions around B and D, and the depletion width increases with the temperature. Just I'm trying to understand this paragraph. Did you understand this paragraph?
Sir, will it be due to the electric field established inside the depletion region, sir?
See, first of all, when temperature increases, the concentration, see, I am telling you, concentration of the minority charges. I mean, before temperature increased, there were some amount of minority charges. Now,
Yes.
these minority charges have increased. Of course, the majority charges will also increase, but I am just talking about the minority charges have increased. So, if these
Yes.
minority charges have increased, okay, then what is the consequence of that?
Then the kinetic energy is also increased.
Kinetic energy is increased. So, why should the depletion layer increase? So, when will the depletion layer increase?
Because they will have like more energy to get inside and reach the depletion layer and get repelled by the other minority charge carrier from the other side.
See, in the depletion region, there are no currents flowing. There
Yes.
are no currents flowing. There are no currents flowing here in this region, depletion region. But why this width will increase?
At higher temperature, it is easier to give out an electrons from the inner bands because more high energy is there. So more and more of minority charges will be created.
So, see now no. You should not beat around the bush. The thickness of the depletion layer will depend upon what? The number of the immobile charge carriers that are created, isn't it?
Yes, sir.
Yes.
So now here you see there are dopant atoms here. There are dopant atoms here. You can see here. You can see here there are holes here. You can see there are holes here. Correct? Now here you see if the temperature increases here, the number of free electrons will also increase. No, this side. Temperature increases, more bonds will break. No,
Yes.
more bonds will break. No.
Yes, sir. Yes.
So more number of free electrons are there. No.
Yes, sir.
So
Yes.
more number of free electrons are there means they will cover more of this dopant ions. See, the depletion layer increases in width means, see, now you please understand the difference here. Here I am showing the ions as plus and this dark hole. Here this and dark hole. I suppose you understand what is hollow rings and solid rings. You understand the significance of that?
Yes.
See here there is plus with this, and here you have got only plus. What is the meaning of this? This plus with this means it still has got an electron, so this atom can still, this atom is still a carrier, but this becomes an ion which is not a carrier, and therefore I am designating it as immobile charge carrier. Agreed?
Yes, sir.
If the depletion layer has to increase, that means this many charges have to be covered. Correct? That means these holes have to disappear. These electrons have to disappear. Correct?
Yes, sir.
So if temperature increases, for these holes to disappear, what do they need? They need electrons.
Yes, sir.
And they need electrons means they need, see, the recombination, hole recombining with the electron, this is what you call it as recombination. The rate of recombination will increase with the increase in concentration. Correct? Concentration of the constituent, that is the concentration of free electrons, concentration of holes. Now, the concentration of the holes here is fixed. The concentration of the holes due to this impurity atoms is fixed. But the concentration of the free electrons here will increase with the increase in the temperature. And therefore, more and more of this will be covered. And therefore, the depletion layer will get extended as it covers this side, and similarly this side. That is the reason why the temperature happens like that. Okay?
When temperature increases, the bonds are broken, sir. And the electrons are given out. When electrons they come out to the conduction factor, there will be some holes also in the expanders.
Let it be there. Let it be. See, that's what I'm trying to tell. See, now a hole created will not affect the. See, I am talking about the effect on these holes, man. If a hole is created here, what will happen to this hole?
Yes.
Got it? No. If a hole is created, nothing. If more number of electrons are created, that will. So that is why this length will get extended. So that is why the depletion layer will get extended. See, these are the questions that will be asked on this topic in the mains. They will not simply end with the, the question is, what happens if, if the doping concentration is increased, what happens? That is the PU question. Okay, maximum CET question. But for mains, you should know the reason why it happens. So that is why I am trying to take you more deeper into this. Okay, clear?
Yes.
Right, as temperature increases. Now the potential difference required to move an electron through an electric field is called barrier potential. Barrier potential of PN junction depends upon the time of consumption. Okay, I will explain this aspect to all of you. Right? Do you know about this potential barrier? See, this curve, and see, all these curves will be useful as we proceed. Now, this curve, as you see here, will be very, very important. I mean, using that, we can explain some phenomena. That is precisely what I want to tell you. Okay? Now, the potential, see, what is this potential energy curve, correct? Potential curve, we call it as potential curve. What is the significance of it? Come on, tell me, what is the significance of it?
If any electron electron wants to move through this diode, it has to pass through this potential in there.
See, what is that you are telling, man? You have to explain that. You have to explain that.
So due to the interactions,
No, it's not interaction. It's not interaction. It's
the
not
field, due to the fields,
due to?
the opposing fields.
No, it's not like that. Huh? See, now look at the word potential barrier. Why did they use potential barrier?
Because it is preventing something, sir.
How that concept of barrier has come?
Sir, because the electric field that will be established, sir, it will.
No, don't assume things and start giving answers. You have to completely understand it and explain to you.
Sir, immobile charge carriers will be present in the depletion region. Sir.
No, that is not non-consequent. That you should not go ahead. Now using the depletion, why depletion layer is created, what is depletion layer, and what is the nature of that. From that point we have come to this. From this graph we have come to this. From this graph we have come to this. Now what is the significance of this? Now again don't start explaining how the potential energy barrier is created. No. Significance of that means, you see, try to understand. See, you have gone through this course in your college. Okay. Now understand this very carefully. Now I am standing here. I have got a line here. I got a line. Can you imagine a line here?
Yes, sir.
Yes, sir.
Now you see, this is Earth. Okay, and I am drawing one fictitious line here. Okay, this is Earth and one fictitious line. What is this line? I mean, what is it signifying here? This line is at a height h above Earth.
All the points at that line, on that line we have the same potential.
Excellent. So you see, you are on top. So the gravitational potential of that will be GH. Agree? Potential energy is mgh. It is GH. Correct?
Yes.
Right. Okay. So that means now if you keep a unit mass here, its potential energy will be 1 into GH. And if you keep mass m here, then its potential energy will be mgh. Correct?
Yes.
Now I will have now mass m here. All these are mass m. Okay. Now I will throw this with velocity v1. I will throw this velocity v2. I will throw this velocity v3, v4, so on and so forth. Now what happened to this v4, v5, v6, v7? So these are different velocities with which I throw the masses. What will happen to each one of them if I throw them?
Decelerate.
Okay. Continue. I want many answers. Everybody participate. What will happen? Use the signs and answer. I have got different same mass but different velocities. What will happen to them? Look at this diagram and try to explain.
So what would like? What do you want to like? What are essence like?
You should build a story. See, this is the ground on which I have got mass m, and this is given velocity v1, this is given velocity v2, this is given velocity v3, this is given v4, this is given v5, this is given v6 velocities. What will happen to them? I am throwing it.
They all will reach.
They all will
reach different maximum heights.
Different maximum heights. Okay, good abstraction. So, with respect to the diagram that I have given, what is the best answer that you can give? The best answer you can give is, can you now see? Hello?
Yes, sir.
Now, the kinetic energy of each one of them will be half m v square. So this will be half m1 square, v2 square, v3 square, v6 square. Understood? The kinetic energy of each one of them will be different. Correct? Now, say for example, half m v1 square. If half m v1 square is less than mgh, then what happens? This will go here and come back. Correct now?
Yes.
So those of which whose half mv square is greater than mgh, they will pass this line and compute. Correct now?
Yes.
Now you see, what is this line? Potential energy barrier. So this is the significance of this. So those of the particles here whose kinetic energies were greater than the barrier energy, they were able to overcome, surmount that barrier and go beyond. Okay? So in this context, you see here, if there is a hole, see there is a hole. The hole, say for some reason it has absorbed some energy. If the energy of this hole is greater than this, then this hole is capable of going this way. Got it?
Yes, sir.
See, the idea of this potential energy barrier, man.
Yes, sir.
That is the idea behind this. So, this is the graph for hole. For hole, this is the potential energy barrier. For electron, how will be the potential energy barrier? That is, for electron, it has to come from this side to this side. It will be ulta.
Yes.
It will be ulta of this, isn't it? It will be ulta of this. This will be what? This will be how? This side. So this is for the pole. For electron, inverse, mirror image of this. Mirror image of this. Got it? Like this. Okay. So that is the significance of this potential energy barrier. So therefore, now what it is trying to explain to you here is, see, now the holes initially diffused. Okay, because the potential energy barrier was not yet built. Right? Once the depletion layer is formed, then the potential energy barrier got established like this. Now, once it has got established, if at all a hole wants to cross from here to here, it just cannot cross unless it has got this sufficient energy to cross. That is the idea behind this. Got it?
Yes.
So you see, all this is important. All this is now very important. All these concepts are important to answer many questions and to explain many further phenomena. Okay, that is the significance of this potential energy barrier. See, that is what I am trying to tell you. Simply don't read something and say I have understood everything. Okay, you have to go deeper into it. Then only you can answer the questions. Then only you can understand higher concepts and higher phenomena. Otherwise, it's of no use. Okay. So therefore, you see the potential difference. This is approximate. The PN junction depends upon the type. So the potential. See, that means now. You see, that means now here. Now a hole will have the charge of the hole is E, and supposing it is silicon, then the energy, the kinetic energy of the hole here should be E into 0.7 volts. Then this energy, that is the kinetic energy of this should be equal to or greater than this value. Then this hole can go here. Okay, otherwise it cannot go here. Okay, that's the idea behind this. Okay. Now, width of the depletion layer approximately 10 to the power of -6. Okay, I'll just take till 9:30. Please excuse me. As doping increases, the depletion layer decreases. I have explained. As the temperature is increased, the depletion layer also increases. That also I will explain. The PN junction unohmic due to non-linear relation between I and V. Okay. Now, did you understand this third point? Unohmic means what? Unohmic means, you see, Now ohmic means, see here you see, yes, tell me.
So before, whatever potential is applied across the junction cell, unless it crosses the potential barrier, no current can flow through it.
Arey, yaar, I have not yet biased it and all, yaar. It is just, see, have I given any external voltage? Have I given any external voltage as it?
Okay.
Around, see, you should be cool. So, I am asking a question. What do you mean with unohmic? Ohmic and unohmic. What is the difference?
Sir, ohmic, which obey Ohm's laws.
Means what?
Unohmic?
Means what? Means supposing you have taken a material, right? Some material, I don't know what is it. Now you are measuring the potential difference across this. Okay? And you are measuring the change in the current. So there is a change in the current and there is a change in the potential difference across this. Correct? Okay.
Yes.
And now if you see, that is, you are increasing the current by delta V, and at the same time you are seeing by how much is delta V increasing. So you will get a plot of what? I mean, you will tabulate delta V and delta I. Okay? And then you will perform delta V by delta I. Okay, you will perform delta V by delta I. You will perform. So you will get many readings here, you will get many readings here. Right? Hello, are you with me?
Yes, sir.
If in this column, if this value, see, you will get value A, B, C, D like this. If now in this column, if A is equal to B is equal to C is equal to D and so on, that means what? You will get a plot of V versus I. This plot will be a straight line. Got it?
Yes, sir.
So that means now this material, if you go through this tabulation and then if you plot, if you get a V versus I characteristic like this, then this characteristic is called linear, and therefore this material is ohmic. Now supposing you plot and you don't get these values, and you plot these values, then you will get a graph like this or like this. Then that means it is non-linear and it is unohmic. Understood the difference?
Yes, sir.
Right. Now the barrier potential for germanium is 0.3, for silicon is 0.6. The electric field produced due to barrier is of the order of 10 to the power of 5 volts per meter. This field prevents respective majority carrier from crossing the barrier. Okay? Fine. Now, diffusion current from P to N, drift current from N to P side, there is no biasing. Diffusion current is equal to drift current. Many wonderful graphs here. What I want to tell you is, see, now this is P and this is N side. The current due to P, on N side, and there is also current in the N side, the current due to electrons. You understood this symbol? The whole current in N side, the electron current in N side. Did you get it?
Yes.
Hello?
Yes, sir.
So now, you see, the whole current in N side, this whole in N side will be one component of the current, and the other component will be what? The electron in the N side. Why? Because you see, now the diffusion means what? The holes have entered here and the holes are trying to diffuse to the right. And the electrons, and on this side only I am telling you. See, here due to the charge density gradient, there is diffusion current. And this one, INN. What is INN here? The majority charges flowing in the majority region.
Yes.
Majority charges flowing in the majority region, which is minority charges in the majority region. Similarly, this side you are going to get INP and IPP. This side. These are the two components.
Yes.
Now, under thermal equilibrium condition, this current is also there, this current is also there. Do you agree?
Yes.
This current is because the holes came here and they started moving. This current is because the free electrons were here and they are coming towards this junction and then they are going inside. But the passage of this in this, I am showing it as IN. Got it?
Yes.
So therefore now, both are due to diffusion only. Both are due to diffusion. No doubt about it. So therefore now, at any point, that is, you take at this point, or 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 this. Okay, I'm just showing you this. So what will be the sum total of these two?
It will be the sums.
It simply be the sum. That is, it will be a value other than 0.
Yes.
Sure? Under thermal equilibrium. Under
thermal equilibrium.
It should be? It should be 0,
It
man.
cannot be 0.
Huh?
No, sir, it cannot be 0. Anytime.
It cannot be 0.
Yes.
Right?
So, both the currents are in same directions. The net flow is towards the right side. Net flow of charge is towards the right side. That way, yes.
Only one student is trying to answer. Come on, everybody think. So therefore, you see, now you have understood what is diffusion current and drift current. Hello? So now I said the under thermal equilibrium condition, I have already defined there and told that the diffusion current will be equal to drift current. Okay, they will be equal and opposite and under thermal equilibrium condition. So the net current will be 0. Got it? You see, you cannot create perpetual energy. Understand? You cannot create perpetual energy. Understood? That is the basic rule. And therefore, you see, if you take a semiconductor material, say P and N type, okay. See, after equilibrium is achieved, what did I say? After equilibrium is achieved, thermal equilibrium is achieved. So at any point, if you see the current, it should be 0. There cannot be perpetual energy. Got it?
Yes.
So that is precisely what I am trying to explain to you. Okay? Capture. Anyway, some numericals are there. There I will make the point much more clear. I think you know the symbol of a diode, P and N type semiconductor diode. Okay, hello, I am showing you the symbols of this. And when you go to the market, if you ask a diode, you will get it like this. There is a silver band which says that it is, this point is cathode, this point is anode. Okay? Hello? Hello?
Yes.
Now, what is the significance? What is the significance? See, usually we write an arrow like this, no? We write an arrow like this. Okay, to say that you go in this way. Correct, no? So what is the significance of this? Why have they chosen this symbol? See, it has got to do a lot of, you have got to understand that also. because when you understand transistors and all this will become important. So here you see, basically now we were using this symbol to show direction. Correct? So here the thumb rule is, if you forward bias this, that is you connect a battery here like this, that is if you forward bias this, the direction in which the conventional current goes is the direction of this, is the direction that is chosen. Correct?
Yes.
Okay? And simply this is the direction, we have chosen this line just to make it look like a direction. That's the idea. Correct? Now when you are drawing, you have to...
Can we say that it...
What?
Sir, can we say that it has one triangle line also to show the junction?
Triangle and a line?
There is a junction between P and N.
Yes, you can take it.
That connecting point between triangle and...
Yes, you can take it. You can take it. Correct. And now when you draw this, you better be careful. Don't do any design like this and all. Because this is the symbol for something else. Okay? Or you do something like this. If you do something like this, this is a symbol for something else. Or if you do like this. Okay? Right? This is a symbol for something else. So don't do any circus there, So it is just a straight line like this. Okay? Right. Now I have to discuss forward bias, but I think it is time up. I will stop. Tomorrow we will continue.